Welcome, everybody. We are Scott Bruce and myself, Eduardo Madrid. We are coming to share with you an interesting story about the implementation of a fundamental data structure that yielded some interesting results in terms of performance. Let me introduce to you my former coworker, dear friend of mine, Scott Bruce. He has worked at Google for many years. Then we coincided at Snap. As a matter of fact, he's the person who brought me into Snap. And even though as early as May of this year, we were still both coworkers at Snap, it turns out that we are not anymore. And the good news for the community is that now we had the freedom to continue this work entirely open source and take it to the next level. What we're going to show is what we have been doing since I was able to present an introductory material on the Robin Hood hash table. And now it is fully open source and we can share all of the details with the entirety of the community. Scott?
Hi, I'm Scott Bruce, first time presenting at CppCon. I'm very excited to present these slides to you. I'd like to introduce my partner, Eduardo Madrid. He snapped out of Snap recently. He's working on open source with me and doing some consulting. He used to work in fintech. He is one of the best C++ programmers and thinkers I know. And I'm honored to work on this presentation and this work with him.
Thank you.
So we're going to talk about the design and implementation of a fast hash table. First, we need to know what is required for fast hash tables and high-performant programming in general. You have to have a locality-friendly algorithm. If you do not have a locality-friendly algorithm, your code will not be fast. Cache lines are extraordinarily expensive. Fetching them takes a long time. You have to do some sort of parallel computation. For hash tables, that usually turns out to be comparing keys in parallel somehow and discarding possible matches as fast as possible. Writing a for loop that checks every key individually is just not going to be fast enough. You need an efficient encoding of metadata. Metadata here means whatever isn't your keys and values. In most traditional hash tables, that's the hash that you may store in some cache or some structure. For advanced hash tables, it's a variety of things. We'll start with a quick hash table briefing. Please.
Yes, so there are basically two types of hash tables. Those that use the open addressing and more colloquially chaining, and those that have closed addressing or more colloquially, the other way around. Closed addressing is chaining and open addressing is probing. So what does it mean, chaining? That you have a series of slots and the slots become sets of more than one element if there are collisions. If more than one key wants to go into a particular slot in the table, then the slot becomes a set to hold as many individual keys as are colliding into that slot. In the case of probing, it's different. You have the entirety of the storage available to all of the keys that are going to be participating in the table. And then the complication is what you're going to do to keep track of how far you have to search when you are not finding the key that you're looking for and so on, okay? It turns out that the chaining hash tables have the really strong problem that they have very bad locality. Because of the node interface and other reasons, the design of the standard unordered map unfortunately requires pretty much to use a chaining design. But we had the freedom to stray away from the standard unordered map and do other things. And what we have chosen is to use the Robin Hood invariant of probing hash tables. So the things to bear in mind when we are implementing top performance hash tables is that in general, we cannot rely that our keys are going to be simple types to compare, such as, for example, integers. They can be, for example, strings. And we cannot rely on the full key equality comparisons to be inexpensive. Therefore, we had to do something. construct some form of proxy so that we can cheaply make comparisons that have a very high probability of succeeding, or said in another way, low probability of both false positives and false negatives. For people interested in hash tables, we want to convert the keys into a numeric code, and we want that conversion to have a lot of entropy. Entropy is unexpectedness. So what we achieve with a metadata that captures a lot of entropy is that the false positive rates and false negative rates drop exponentially on the number of bits for the encoding. That's the best that we can hope for. And this is absolutely vital to achieve performance. So I'm going to let Scott introduce to you the Robinhood fundamentals.
So Robinhood hash tables are a linearly probed hash table that tries to avoid the failure mode of a linear probed hash table, which is your entire hash table fills up, and every time you do a lookup, you have to scan the whole table. We do this by keeping track of the probe sequence length. So we have some home index that a slot wants to map to. We have some actual index that it ends up mapping to. We keep track of the length from its home index, and we use this to bound the work we do on find and choose the place we insert on insert. If that didn't make sense, I have visuals. Here we have an insertion. So imagine your element that you are inserting is 25, and its home index is the third index on this slide. If the table is empty, you go immediately to your home index, and you record your probe sequence length of 1. We encode an empty cell as having a probe sequence length of 0. Now, if you go to insert and the table contains elements in your home index, you have to start your scan. So you begin your scan at your home index, in this case, the third index. You see a probe sequence length of 1, which matches your probe sequence length, but there's a different key involved. So you go to the next one, you see that it's full. You go to the next one, you see that it's full. At this point, your probe sequence length is 3. And so your probe sequence length is equal or greater to the probe sequence length in the table, which means you cannot yet insert. When we go to the 14,1 offset, suddenly the probe sequence length in the table is richer, that is closer to its home than your probe sequence length, which is 4. You're 4 away from home, it's 1 away from home, and whoever is closest to their home is obviously richer. So you evict them, force them to move farther away from their home, and take their slot.
That is the essence of Robinhood, because you're stealing from the richer to give it to the poorer.
Absolutely, which we strongly approve of. And so now you have to insert that 14,1. 14,1 looks at 22,2, sees that it is poorer, has to go to the next index. And then with probe sequence length of 3, it inserts at the 6th index, because that one has a probe sequence length of 0, which is richer. Hopefully this helps with the idea of probe sequence length, which is extraordinarily key to this entire thing. If you're doing a find, the procedure works exactly as before. If the item is missing, you start looking at your home index, and you compare elements until you find either the element you are looking for or a probe sequence length that is richer than yours. The moment you see someone richer, you know that the find terminates, because if you would have been in the table, you would have been there. You will be nowhere else. For a find where the item is present, you simply scan the table until you see an exact match of your value, your hash code, and your probe sequence length. Deletions. Lots of linearly probed tables use tombstones for their deletions. Robinhood is more adiabatic than that. So, first you do a find. You find the index of your element. Then you find the end of that block, which is defined as the first element after you that has a 0 or a 1. because at that point, the collision chain has resolved itself. So you only need to shift those things back. So here, removing the 25, 4 element results in moving, that slide is an error, I apologize. That should be 22, 1, 14, 2. It results in moving those 2 elements back, one, like shifting them left, 1 space, and then decrementing their probe sequence lengths.
Yeah, the general idea is that you move them closer to their home because a new position became available. So you pull the entirety of the chain of elements that were behind that deletion until you find either an empty slot that tells you that you don't need to continue, or a key that is already in its home. At the end, if thank you.
Yeah, we have a lot of things to present, and the time is relatively tight. So Robinhood hash tables have very nice properties. The Robinhood invariant, which is this idea that richer things get evicted so that poorer things can be closer to their home, has very, very good locality properties. Your maximum find operation given a non-adversarial hash function is log n of the table size. So a table that is 2 to the 30th.
That'll be a billion elements.
Has a maximum probe sequence length of 30. This is phenomenal, especially if you encode things very well. The other thing that's very nice is that the probe sequence length, you know it can only grow 1 per slot or fall arbitrarily. So this allows us to avoid a few checks later on.
Yes, so the subject of the Robinhood hash tables is rather complicated. So I'm thinking that we can mix the introduction of the Robinhood with other designs and other people that have also implemented the Robinhood. In particular, if you guys want to read code that is understandable in terms of how a Robinhood invariant might be implemented, I will direct you to Malte Skarupke's implementation. He did a phenomenally good, very thorough and comprehensive presentation about the whole thing about hashing. Thank you very much, Malte, at C++ Now 2018. And the only thing that I can say about the work that he did is that he made a few things that seem to look like it is the end of a road in terms of performance. As a matter of fact, at the end of his presentation and the work that he did later, he went away from Robinhood because he couldn't get more performance out of it. The other implementation that is probably the most popular, because everybody that I have talked about Robinhood has pointed me to Martinus, is Martinus, the GitHub Martinus. Because it is the most popular, it is very production ready. And we studied it, and when we were studying it about performance mechanisms, I think that we identified a critical bug, but that comes about something that we're going to make an emphasis on later in the presentation, which is all of this performance, top performance code has been done compressing a stack of abstractions into almost a very thin layer of ad hoc, inflexible, and monolithic code. I hope to persuade you by you looking at our code that we have more or less the same performance at the top, but with very clear separation of abstraction levels. And this is one property that the work that Martinus, I don't quite believe that it has of clear separation of abstraction levels. The other, because Scott has been at Google, I'm going to let him tell you about the Google work on this subject.
So Google did a very good table implementation called a Swiss table. It is it's a linearly probed hash table that takes some bits of some bits of the hash, calls it a tag, hoists it into metadata, packs that metadata together, and then does SIMD operations against that metadata to do fast checks to rule out keys. This allows them to check something like 16 keys at a time with a 1 in, I forget the exact number, 1 in 128 false positive rate, against like a very straightforward linear table implementation. So they might have a collision chain that is 50 or 100 or 500 long, but they're checking them in like 16 at a time, so it goes relatively quickly. It's a very good table implementation. There's also the F14 hash map from Facebook by Nathan Bronson and Shashu. I apologize, I'm sure I got that name wrong. It is a double hash table, but it avoids the overhead of double hashing by chunking in size 14 blocks. This table also hoists tag bits, 14 at a time, and the table is very much written in this extraordinarily compact style that is extraordinarily brittle. It's so non-parameterizable that the number of elements it checks at a time is in the name.
Yeah, STS14. By the way, maybe I should mention that Scott might have a conflict of interest because he works at a company where Nathan Bronson is a coworker. So,
thanks to Nathan Bronson for some feedback on this talk. It was excellent.
Yes, thank you very much.
Design and goals. We have like a very high design target, right? Which is to get extraordinarily high performance, do it with extraordinarily high load factor, design configurable metadata characteristics so you can choose the attributes of your table. And we want to have type erase dynamic tables, which we'll talk about later. The design strategies we use for this is using SWAR for bit parallelization, doing parallel operations on our keys, generic programming to make sure that we keep our abstractions healthy, zero cost abstraction layers so that we can stack those abstractions really high for our understanding and yet still get very good output code. Avoid over-specifying code to give the optimizing compiler room to work, and using improved instruction cost models.
Yes, I believe that this can only be achieved with C++, and it's something that I have been telling you guys for a long time now.
Yes, it's very true. I think he's correct. So SWAR is SIMD within a register. This is a it's not a novel concept. It's been around for probably 15 years. It's something that I don't see used very often. SWAR is a very good abstraction around doing parallel operations against a single register. So SIMD hardware creates hardware lanes that cannot interfere with each other. SWAR as a technique, when used with a generic register, a 64-bit wide register most of the time these days, creates software lanes and then does operations on them. So this provides a lot of power because those lanes can interfere with each other, but it's very fiddly because those lanes can interfere with each other. So why do we use SWAR? SWAR makes things safe. The techniques that we use for getting performance are fiddly, and the optimizing compiler will make different choices on different architectures on how to actually emit instructions that provide that functionality. So this keeps our abstractions healthy. This allows us to specify what we want our code to do, and it allows us to look at our code and have a much better chance of catching bugs by simply reading it.
Yes. So what are the benefits of using this parallelism within normal serial execution? Because the parallelism that we're talking about is like, for example, in 64 bits, a normal integer nowadays, you can have 8 bytes that each one has 8 bits and do parallel computation on each of those elements. Like, for example, a comparison of whether something is greater than the other on a per byte basis. Well, when SWAR is giving us a benefit, what we're doing is executing in parallel all elements at once, so we're achieving true parallel computation performance. Sometimes it gives us the opportunity to implement things that would be cheaper than otherwise. And sometimes when we had to, let's say, iterate over each of the elements in a SWAR, then we're back to entirely serial. And that is more or less about the same cost as not having SWAR at all, right? Therefore, in general, when you use SWAR and the situation calls for it, you are always ahead because sometimes you will get parallelism and sometimes you won't, or sometimes you will be in between, but in general it's beneficial. And the very key word here is doing sets of useful operations. Because if you only had to do one thing, then SWAR is not going to help you. But if you have like a set of things to do, accomplish, and you manage to organize them in a way that can be done in normal integers in parallel, then you're going to be ahead in performance. Okay, we call this SWAR, but we have run some very early experiments of upscaling to proper SIMD registers in the architecture that we're using. And that is looking well. What we're doing on normal integers is scaling just fine. But of course, we had to concentrate on delivering something that the community can see and help us develop. And our focus continues to be SWAR. The really important part of how to achieve performance with C++, in my opinion, is generic programming. The paradigm of generic programming, which is using concepts and applying those concepts. The library that we developed, the SWAR library that we developed for the purposes of PokerBotic 3 years ago and now Robin Hood, has the property that you can see the concepts being applied, okay? The general idea is the phrase that Scott invented yesterday of keeping abstractions healthy. Meaning that you're not going to be losing performance because you're using them, or you're not going to paint yourself into a corner of inflexibility, or that you're going to be misrepresenting the operations that you want to do. And one of the ways in which you can tell that your abstractions are healthy is because they compose naturally.
This is actually a huge deal. I would speculate that I've spent 10% of the hours in my professional career chasing down the bad effects of leaky abstractions, broken abstractions, or abstractions that specify one behavior and do something else.
Yes, the abstractions that we're talking about are those that are optimizer friendly, so that the optimizer can be happy with all of that because it knows so much, and to keep the code comprehensible to us, the programmers, okay? And this is one of the ways in which our code is allowed to not be monolithic. Part of the generic programming is to avoid over-specification of code. You're going to see in the code base, if you feel like going to GitHub, that everything in our code is auto. Sometimes that might be confusing, but the real benefit is that you can change things, and because the compiler is always calculating the types, then you are always going to get a self-consistent type. And if you don't over-specify, then you give the compiler more leeway into what it can do.
So another tool that we used that we think was material in improving the performance of our table is changing the cost model that we use when we think about how performant code is likely to be. Traditional cost models don't really work that great for writing high-performance code. Algorithmically, in a theoretical basis, we almost always use compares as a proxy for how much work will be done by our algorithms. But the moment you actually use this while you are writing code, it's going to fail. The variability instruction cost is too high. In the last 10 or 15 years, maybe, counting cache lines has become an alternate method, or cache line accesses, has become an alternate method of determining how fast your code will be before you run it. It treats all other operations as free. This is unfortunate because if you miss a couple branch predicts in the course of a cache line, you can take more time on the actual code you run than the time you spend fetching a cache line. So it's an extraordinarily insightful thing that cache lines are expensive. And the nature of the memory hierarchy for any given computational system basically guarantees this will be the case. But it's not good enough when it comes to actually running high-performance code, if only because the other instructions are not actually 1/100th of the cost. So we use more of a tiered instruction cost model when we're thinking about our code, We're thinking about how fast our code is likely to be when we run it. There's a tier of operations that are free or nearly free. Bitwise operations often get stacked together in the execution units and end up costing less than 1 instruction per. Additions and subtractions usually cost about 1 instruction per. Multiplies, branch hits, predicted indirect branches, those cost 1 to 3. Divisions and modulos, because a modulo is just a division, cost 40, which is insane. I didn't actually know this until maybe 5 years ago, and I've been doing this for 25 years. One division in the wrong place costs more than your branch missing all the time. Branch misses cost between 10 and 60, depending on the complexity of the branch and like where it happens to happen. L2 cache misses, catch line fetches, cost between 50 and 150. So stacking up an extraordinarily large number of bitwise operations and adds and subtracts may actually be much, much, much cheaper than running a division. So another design objective here was to design for an extraordinarily high load factor. Koolekundis in his Swiss table presentation for Google pointed out that about 4% of Google's RAM is in hash tables. I worked on projects at Google that were effectively put a hash table in memory and use it to do a computation. And the hash table memory usage was the constraining factor on the scale of the problem we could fix. Load factor determines how good your overhead can be for a hash table. If you get the metadata into a very minimal format, then you are bound by your load factor. You can do no better. If you can get up to a 99% load factor, then you just don't have much overhead. If you're forced to use a 50% load factor, as a naive linearly probed table is, you're guaranteed to have a ×2 overhead, which is just prevents you from executing an enormous number of workloads efficiently. We have a very strong design goal to parameterize the table. And for this slide, it means we take some number of bits of probe sequence length and some number of bits of the hash, pull them into the metadata, and then pack them. And you can choose how many of those bits you actually want to use. So F14, everything is fixed. The way we've designed our table, everything is mutable. You can choose to have almost no probe sequence length bits stored, or you can choose to have an enormous number. You can change the total width of that storage. All of these changes help you select a table that is performant for your workload in the cases in which a generic canonical configuration is not performant enough. We also have configurable data layouts. So we have metadata blocks and we have key blocks. Our current implementation separates those. We have some array that contains metadata, and we have some structure that contains keys.
Yes. And the reason for this separation is that it's very important that we work only on the metadata, because working on the metadata is very cheap in general, and defer to actually work with the actual keys and so on when the metadata tells us, yes, now go to the actual store of the metadata, the key data, because there is a very high probability that you actually need to do that.
And so this has been a very performant structure for us, but we believe that other structures will be more performant under other situations. You could interleave the keys and the metadata such that every cache line fetch contains the metadata for 7 keys, and then those 7 keys in the same cache line. There's other metadata configurations that might be useful, so we have the ability to change the underlying metadata of the table at will. And then our final design goal is to have type erasure during runtime so that we can dynamically switch out the implementation that you're using without you noticing for better performance based on observed behavior of your table. This is not implemented yet, but it is possible. So now we'll talk about our implementation details. I have about 10 slides here. So this is a very key slide. This describes how we pack our metadata. So we take a SWAR, which is what we call a register that we are using with the SWAR abstraction. We divide it into a SWAR with sublanes. So there's 2 sublanes for every lane. And we put the probe sequence length in the least significant bits of a given lane. And we put the hoisted hash bits into the most significant bits of a given lane.
Yes, I think that we need to say what the hoisted hash mean. This is when, for example, you invoke a standard hash, that is going to give you a 64-bit code, right? But we don't need all 64 bits to make a quick comparison. We can get away with doing a comparison with only 3 bits, right? Or 4 bits, or whatever we feel. So we have a process to select from the original hash code the bits that we want to hoist to the metadata, okay? And they are going to be representative of the entirety of the hash code.
So we place the PSL bits in the least significant bits. We place the hoisted hash bits into the most significant bits. This allows us to do very rapid comparisons of a potential element we are looking for with the table itself. Specifically, there's a subtle thing here, which is placing the probe sequence length bits in the least significant bits means that when we blit out the hash, we can do cheap comparisons of the probe sequence lengths because the most significant bit is off. We can guarantee it's off. So we can add 1 to that bit and do a subtract. And the result of that is compare. You're guaranteed to have no lane interference. And so you get a full comparison of 8 elements with 1 subtract. And then we also use a subtraction of the most significant bit of every lane encodes a Boolean for that lane. And so using that abstraction means it's very easy to convert any of these comparisons into a Boolean SWAR that has some other nice properties we'll talk about later. Why do we only use probe sequence length bits and hoisted hash bits? We do this because we don't believe there is another way to use those bits that will give us the same exponential benefit in reducing the false positive rate. Every time you add a hoisted hash bit, you clearly get a factor of 2 reduction in false positive rate. Every time you add a PSL bit, you get an expected reduction that might be larger than that because your guaranteed longest chain length is log n, and the probe sequence length encodes that in another log n. So 5 bits, in theory, is enough to encode for a billion element table, given, again, a non-adversarial bit mixer. So when we're doing our lookups, we construct the sharpest needle. And we stab the haystack with it. We feel like this is a nice metaphor. Anyway, so we construct a needle that is the probe sequence length starting from the home index and the hoisted hash bits. So here, the home index is the 0th index. And so the needle has a probe sequence length of 1. And then 2, 3, 4, 5, 6, 7, 8 as normal. And the example haystack, which would be one of the SWAR blocks inside of the table, contains 6 elements. And the one in offset 4 matches. So we just bitwise and those 2 together, do a comparison of 8 sets of metadata for an instruction cost of less than 1 and get our answer. You can see there are places in the table where the probe sequence length matches, but the bits don't match, so it's not a match. You can see there are places where the probe sequence length doesn't match, but the hoisted hash bits do match. Also not a match. But we get one place where there is actually a full match. So we refer to this particular way of doing a find as an aligned find. That is, adjusting 2 SWAR blocks so that the home index is always guaranteed to be the 0th index. We can
go back. This is very important that after the match, immediately after the match in this particular case, you see that the needle is poorer than the haystack, okay?
Thank you.
The needle will be poorer than the haystack. So that means that position is the earliest place where the Robin Hood invariant would be broken, and therefore, that is the termination of this particular find. With this scenario, this needle and this haystack, we know that we have reached a conclusion. Either the potential match that we have identified will lead us to a key that actually compares equal, or the key is not in the table.
Thank you for pointing that out. I should not have forgotten the deadline. If the deadline is not present in this SWAR, if there's no place where the hash table invariant is violated, then we will pull the next SWAR and do this again. The expectation is, again, that this will complete in log n elements. We're referring to 4 bits of hoisted hash and 4 bits of PSL, which is 8 bits of metadata on a 64-bit register, which is 8 lanes. But again, this is all configurable. But with 8 elements per lane, 4 compares will get you to 1 billion elements in your table for your find. Here's an example of a needle that is not aligned, is unaligned. So its home index is at the third of this, or the third position on this SWAR. You can see the match and the deadline occur again by ANDing. So we've done something that we think is interesting, which is break apart the functionality of a hash function or a hash code. Usually we use this for finding an index, and we use it for doing a cheap equality check. So we've broken these into 2 different functions to try and increase the entropy. One of them is scatter, which finds a home index for your element based on its characteristics. The other is hoist, which is execute something and gives you a hash code-like thing, and then pull its hash bits out of it. This allows you to pick the cheapest, worst, non-adversarial bit mixer possible in both cases, because that's all you need. If you want a bit mixer that gives you good avalanche properties, good bit mixing properties, like very good ones, it might cost 3 or 4 multiplies and a bunch of other operations. If you just want a really bad mixer that's not terrible, you can do it in like 1 or 2.
Okay, so one of the goals is to reduce dramatically the number of conditional branches that our code is going to be represented as the assembler, okay? And why are we so keen on reducing conditional branching? Because we want to reduce the pressure on the branch predictor. That way we get 2 really important characteristics for our code. Number 1, the code is deterministic in the sense that it always executes the same amount of work and it has about the same delays, which predictability is a nice property. I should know because I'm a Bitcoiner, so the volatility of Bitcoin is difficult to deal with. The volatility of the performance of executing code when we're talking of high performance is difficult to deal with too, okay? So that predictability is important. And the other thing is that because we are frugal on our usage of resources that impact the performance of everybody else in the same execution platform, so just for example, the branch predictor, well, we are being kind to the rest of the execution environment, and in general, I hope that our implementation is going to improve the performance, not just of the part of hash table, but of the entirety of the execution environment.
And we do have evidence for this. The F14 productionization documents that were published, and in conversations with the authors, they found that there were ways they could make changes to F14 that resulted in it benchmarking worse, using less hardware resources, but getting a global increase in throughput on, effectively the instrumentation of the entire Facebook computational workload. Right, so we have strong expectation that doing this is exceptionally beneficial.
Yes. By the way, we have the Compiler Explorer links at the end that we're going to explain. We had to get there, so I know there's stuff on Friday of the conference, but we will get there and show you how our code is very frugal on execution resources. Because of the model of costs that we have, we de facto have band divisions. And this is the only reason for why our code cannot configure, like for example, a SWAR register that has a lane size of 9 bits so that you can have 7 of them in a SWAR. Because then we will have to use more multiplications for emulating divisions by a compile time constant and sometimes a proper true division. So, but we are investigating how to achieve this because we have some ways to deal with that. But it's not like our templates are not capable of doing it. It's just like the performance won't be there without extra work. And well, this is in the code that we see in the example. This is for the finding because we want to guarantee that on our first match attempt, we're going to use the entirety of the SWAR register. We don't want what was in the slide, this slide, that we are starting in the middle of the SWAR register, so we are losing the opportunity to make 3 comparisons. We are doing a combination of the current SWAR that we're looking at into the haystack and the next one. And for that, we need to make a combination, right? But to make the result, from one side, we'll have to move to the right, and from the other side, we'll have to move to the left, depending on exactly where the position is. And we saw that we don't need to make a conditional branch here. We just calculate both things, do the shifting of both things unconditionally, and put them together, and that'll work because of the architecture that we have.
I actually find this to be an incredible result, because if you'd have asked me 15 years ago, always trust the branch predictor would have been my answer. But it turns out that there are times in which if you just do both sides of the computation and smush them together, it's so cheap to do that keeping branches out of the equation is wildly faster.
Yes. Okay. I was explaining that the first comparison against the haystack, once we assemble a needle, we want to make a comparison against the haystack that is using the full length of the SWAR. So we need to simulate that the SWAR is, the haystack is aligned to our particular find. And what we're doing is to combine them and like the slide says, we're just doing a prioritization of the first comparison. And the cost of that is a bit of work of fetching and combining with shifts.
One point about that last slide that is important. The reason we choose to align our SWARs on find is because if you select a random position in the table, which for any given find is probably what's happening, you're likely to hit in the middle of a SWAR.
Yes.
So if you start from there, you're losing half of your SWAR power. And it costs like 3 shifts to get the whole power of it at the start and like 3 shifts at the end. So we're trading something like 5 or 8 shifts to delay a branch to where we may not need it and to make it more effective across all the latter iterations of the SWAR.
Yes, thank you. Okay. In the case of the insertion, we are faced with a different scenario in which SWAR loses a little bit of its benefit, because every time that you find a place to insert the key that you are attempting to insert, either an eviction or the actual key that you wanted to insert, this is what we termed a causality horizon, that you have to stop and do the analysis of whether you're going to do the insertion there and do the insertion and so on, right? So it is not profitable to do the implementation of insertion in a simulation of the thing being aligned. Just what we're trying to convey to you here is that if you are very systematic about the choices that you have, you will be doing decisions like, simulating that the data is aligned is going to be beneficial in this opportunity, but in this other opportunity won't be. You have to be very systematic and so on. And that is what highlights the benefit of having very good abstractions that you can combine together without losing performance, because you'll have to decide on these things, and if you would be doing it manually, you would get crazy. Okay.
So evictions happen when you do an insert and there's a collision. You end up with eviction chains on longer tables. Those eviction chains can reach the entire size of the table, and we have seen that happen. So it is more prefetch friendly and cheaper to journal the key moves and then apply them at the end, or apply them after some large number of them have been created. Metadata moves, you can journal them or you can apply them optimistically. If you journal them, then you get to have more exception safety. If you apply them optimistically, you get to have more performance. Right now, we're journaling both, There's an optimization available there in the future, but even with extraordinarily high eviction chain lengths, insertion still performs performantly because the journals themselves are extraordinarily prefetch friendly. You're just scanning through memory and blitting in some data. So, we talked about this a little bit before, but division is wildly expensive and we shouldn't do it. It slows down lane widths that are not a power of 2 enough that you can see it in benchmarks. At some point in the future, we think it's possible for us to get the performance close enough that we'll be able to benchmark those and find a good enough performance that it would be a reasonable choice, which would be fantastic because sometimes 10 bits is the right amount. But generally, our code has maybe 3 or 4 divisions in it on the hot path for for find, which is not very many. We talked about deletion by shifting back. The main thing I want to say here is tombstones destroy performance, especially there's a very common table load which is I want to add a bunch of keys and then I want to start deleting keys and looking up keys and I want to do that forever. If you are using tombstones, that particular scenario will have just horrific performance for you. So resizing these tables is very interesting. The standard resize works just fine. You can have a table of size in, you can make it beat size 2 in, you can rehash everything, find its home index again, rehoist its bits, reinsert it, you're good to go. However, you don't have to. For a given key insertion, the table layout is deterministic. If you don't change the size of the table and you just run out of probe sequence length bits, you can just steal one of the hash table bits. You blit out all the least significant bits of the hoisted hash function, and then tell the table that its probe sequence length is just 1 more bit than it used to be, and it works. Suddenly your probe sequence length is longer. You can also grow the table by mem copying. If you just add 2 more bits to the probe sequence length and mem copy to a wider table, then you don't have to rehash anything. If you add bits to the hash code, the hoisted hash, and then mem copy the table, you'll have to rehoist the bits, but you won't have to find the home index of anything again because all the home indexes will be the same.
Yes.
It's a very interesting thing that you can effectively grow the table, grow its capacity in several different dimensions, and some of those involve effectively no extra work. All right, so now we're going to talk about our results. I'm very excited about our results. Not going to lie.
Okay, so of course, we have the open source code for this. We don't have the time to show it, but the thing that we're doing here is like the title of the element says, or the slide says, we have an element count of 300,000 elements, okay? And we see that the trusty friend of the unordered map on the standard library has a load factor of about 85%, and we basically have a full table load factor, okay? And the results are that the baseline of just running the hashes on the integers, by the way, this is a table that maps integers to integers, and what we're doing is to compute the histogram of the occurrences of the elements in a stream, and this slide is for always the element that we are going to get in the random stream is always going to be found in the table. So we have that unordered map takes 91 milliseconds on this computer, and the Robin Hood implementation that we worked on is better than a factor of 10 performance. And just for comparison's sake, standard map takes about 300 milliseconds. One takeaway from this slide is that we are much better to the unordered map implementation in the standard library that we're using than the unordered map is to the tree-based map. Now, if we have all misses, by the way, please make note of the times. Unordered map is 91 milliseconds, and Robinhood is 6.5 milliseconds. And unordered map gets better when it is able to, when it cannot find the elements, and our implementation gets more or less the same range of performance. Okay, the difference in performance is almost a scale, an order of magnitude. Now, we have been doing something that is like the most disadvantageous comparison of performance for our hash table, which is very easy to compare keys, which are integers, right? Because we go through the trouble of constructing the hoisted hash bits that are a representation of the original key and so on. So let's see, let's give it an example. Let's say that we have from The Turn of the Screw, a novel that I like, we just get the English words in that text and run them through the histogram generator. And we see that on the average, the Robinhood implementation is substantially faster than the unordered map. And the characteristic of this slide is that the relation of insertions to findings is about 10 to 1, because The Turn of the Screw is on the order of 50,000 words, I think, and it has 5,000 different words in it. Now this is a slide of insertion. I must say that I didn't put a very strong effort into squeezing all of the available performance to me while implementing insertion, but it doesn't matter what is the size of the table, the number of elements, the configurations of for example, in this particular case, I can show you that we were devoting 6 bits to the probe sequence length or 5 bits to the probe sequence length and so on. And we got comprehensively better performance.
Before we move on, I want to point out one thing about the benchmarks that I really like. We had a design goal of hitting a very high load factor with very good performance. The load factor here is 99.9%. There's 300,000 elements on the table, and there's 300,168 slots in the table. I almost don't believe it's true. It's so good.
Yeah, but it is true. You can see the chains on the metadata and so on, and yeah. But
it looks
hard
correct.
To believe.
But in a week or two, maybe try to go break our code, please.
Okay, so what we were talking about, how difficult it is to get these things right and so on, right? First, let us show you a word of caution that the compilers sometimes get crazy on you, okay? And how do I increase the font size? On the browser? Okay, it's the same. Right. I hope that you guys are able to see this, okay? But one thing that I think that I am not getting the slide that I wanted. Sorry about the delay. Well, allow me. So there are some things that
no, you gotta. What are you looking for?
Yes, go to the bottom of the code pane. So that is the example, all right? To the very bottom. Very bottom. Okay, there. So what we're doing here is to attempt to find a key in a table. Okay, and the table is a canonical front end with 8,000 elements and the parameters of 5 and 3, 5 bits for the PSL per metadata entry and 3 hoisted hash bits. And what we see is that the compiler does things that are annoying. Like, for example, it uses the SSE registers for some stack alignment work, and instead of inlining the things in the way that we wanted, it went ahead and did non-inlined calls, like, for example, this one of calling the find misaligned instead of having inline this code and so on. So you had to spend a substantial amount of work and effort to try to understand what's going on, why the compiler is not cooperating. So it's part of the work that you had to do, because we don't want to lie to people and say, oh no, everything is Dory and dandy, but it is doable. Now, with a very small set of modifications, what we find is that the lining happened, and we don't see the annoying stack management things that were happening before. Of course, this is far too complicated to explain the constraints of our time, but I can show you and satisfy the promise that I gave you on proving to you that the code is basically what I would call autistic, in the sense that it doesn't require branch prediction. It is just computing, and I'm done. So this is the most important primitive in all of our code, I would believe, because it is the thing potential matches. Potential matches is what, from a constructed needle, will make, in this particular example, 8 comparisons in parallel against the haystack. And this is the implementation. So this is all of the expense of executing a comparison against 8 keys in 8 slots in the haystack. So as you can see, it is all binary operations, loading immediate constants, and unconditionally returning. And for good measure, I'm just going to spend a few seconds on something that is truly important, which is the thing that from a needle will go and compare against the haystack and determine whether in the haystack the invariant of Robin Hood is broken at some place, which means that the needle would be poorer than the probe sequence length in the haystack. And this is it.
I find it exceptional that we have about 20 cheap instructions to do that operation.
For 8 comparisons in parallel.
Just something like 3 at a time, which is kind of ridiculous. I can go over future work in about 50 seconds. You can rotate keys to make them more optimal because the chains all have the same PSL, so anything that goes to the same home index can be swapped with any other element of that index. The Rust Robin Hood table had like a quadratic copy execution bug. We think we don't have that bug because we have like a different way of generating HB. We do want to productionize this to the point where it is solid enough for real use, to the point that like you could use it inside of Google. It'll take us a while. Benchmarks are lies. And the end goal is to have a type erase dynamically configured auto-balancing hash table that's suitable for an enormously wide range of workloads. This may take a long time. Thank you all.
Yep. Well, if I still can insert a comment, the reason for why our comparisons are against the unordered map is because if we would do it against F14 or app sales, hash tables, etc., it would be much harder for you guys to run this. And we are not claiming at the moment to be production ready. We just show you the performance of the primitives and the work that we have done so far.
I know our time is up, but any questions?
I have a question from online. It is against one of your early slides. It says, sorry, but the second element of the pair, 14,3, something like the bucket ID?
That was the SWAR element that I said had a mistake in it.
Yes.
Well, the question is that the bucket ID of the key 14?
You also had a question earlier. Do you still want to ask your question?
It was about this, yeah, it was about whether or not, so internationally should be the 22,1.
Uh-huh.
Yeah, exactly. I made this, sorry, I thought I said this while I was presenting it. I must not have been clear. And then I tried to edit it in place and failed.
That is great. That means that the audience, among other things, was actually awake and giving us attention.
I mean, I have definitely presented before and had someone fall asleep on me in the front row. It was hilarious.
So does that shift down all of those elements when that happens?
Wait, did I just do the same? I'm sorry, this is the wrong slide. This is correct. The deletion slide is incorrect. Yes, it just drags the elements down.
Pulls the chain. Pulls the chain after it. And the termination of that chain is either an empty slot or a key that is in its home index. The condition would be the probe sequence length of 0 or 1.
Apologies for that. This is correct now.
So first off, Eduardo, I'll say this, that I think I've been to every talk you've done, and I find that I learn something every single time.
Thank you.
And I really appreciate it. I have like a dozen questions, so I won't ask them all because I don't have time. So I guess I'll just pick one. Typically, Robinhood-based hash tables are optimal for building a table and then doing lots of searches. How does your table perform in a situation where you're doing lots of add short-lived operations and then deletes?
I want to answer this one. I think it does great. Our insertion is very fast. Deletion chains are very fast. But we haven't got extensive benchmarks on that use case yet, but we will have them. But we don't expect them to be bad.
Yes. Like I was trying to say earlier, I didn't put a lot of effort into the performance of insertion because I just wanted the insertion to be able to measure the finding. And it ended up much better than I thought. And the reason is exactly what Scott said, that it is so memory architecture, memory hierarchy friendly, that you are always working on the hot path on an easily to prefetch thing because, an insertion is to find the place, is just to go forward in memory. And once you have inserted, it is to do the opposite direction for applying the journal of key moves and metadata updates if you're updating the metadata, you see? So you construct a journal from the perspective of if the memory progresses in that direction, you are finding the places where you're going to insert and building the journal. And when you're applying the journal, you are reverting the direction. It's a stack. So it is extraordinarily memory hierarchy friendly.
Thank you very much.
You're welcome.
Other questions?
Thank you for the question.
Until they throw us off the stage. Why did we choose to pull the chain down instead of swapping the element at the back? So per that later slide, I mentioned that you can do that swap if they're a member of the same home index. It's not guaranteed that the thing at the end is a member of the same home index. However, I'm going to try that. You could find one that is the home index, swap it, and then keep going. Yeah.
Yes.
It would shorten your deletion chain materially. So thank you.
Thank you for the question. The plug is being plugged on us. So.
All right. Thank you all.